Hello and welcome. Today we're going to be discussing the question strange function. In this problem, we are given a function f of x such that if x consists entirely of zeros and ones, then f of x returns x minus 1. Otherwise, f of x returns the value x after taking each digit mod 2. And what we want to know in this question is, given a value of x, how many times will we need to apply the function f of x in order to reach 0? Let's take a look at an example. So in this example, we have the input x is equal to 4,270. In this number, we can see that there are digits that are not 0 and 1. So the very first thing we're going to do is we're going to mod each digit by 2. So all of the even digits become 0, and all of the odd digits become 1. So after one application of our function, 4,270 becomes the number 10. I'm just keeping the leading zeros to be as clear as possible here. Then we're going to apply the function to 10. 10 consists entirely of zeros and ones, so we simply subtract 1 and we get 9. When we apply the function to 9, we're going to mod all the digits by 2, so we get the number 1. Applying the function to the value 1 achieves the value 0. So we can see that 4 applications of the function are required to reduce the number 4,270 to 0. And we want to be able to solve this for very large values of x. In particular, we're told that x can go up to 10 to the power of 200,000. Since x is so large here, brute force will not get full credit, and we have to find a pattern in order to solve this problem. And when I want to search for a pattern in a USACO question, my strategy is always going to be a test case bash. In our test case bash here, the first thing that we want to observe is that we only need to analyze strings formed by zeros and ones. That's because any string that contains digits that aren't 0 and 1 will turn into a string of zeros and ones after at most one operation. So we'll apply the function and then we'll get a string of zeros and ones, and then we can see how many operations from there does it take in order to reach 0. So by only analyzing strings of zeros and ones, we can reduce the work we have to do by a significant factor. So let's start by analyzing a few test cases. I'm just going to write out a few data points here. So when x is 1, we require one operation. When x is 10, we require 3 operations. And when x is 100, we require 6 operations. So far, we're probably not seeing a pattern. So let's get some more data. We're going to now look at x is 1,000. That requires 12 operations. And when x is 10,000, that requires 24. If it's 100,000, it's 48. The next one is 96. And I'd like you to pause for a moment and think, what is going to be the next number in our pattern here? If you guessed 192, you're correct, because what happens to the number? Well, after 3, each time I add a 0 to this value, the number's doubling, right? From 12 to 24 to 48 to 96 to 192. It doubles each time. And you might say, well, how are we solving all of these test cases? During the exam, when I wanted to analyze this data, since I knew that I was going to be analyzing a lot of test cases in this question, the very first thing I did was actually code up the brute force algorithm so that I could very quickly check what would be the result when I plugged in various numbers. So I used the partial credit solution to the problem as a way to get data, to analyze that data for a pattern, and then that pattern was going to allow me to find the full credit solution. So if you're thinking, well, how do I actually get these numbers? You're going to want to implement some brute force process that actually simulates applying the function over and over. And for these small values of x, you can see that the number of operations needed isn't too large. So you should be able to brute force over these test cases. All right, so our general pattern is looking like, well, the numbers are doubling every time we add a new digit. So let's add a few more test cases to the mix here. So again, now I'm going to be adding a bunch of zeros and then a 1 at the end. And you can see that the answer remains fairly similar. It's roughly doubling each time. However, what you'll notice is when I add a 1 at the end, the operation is 1 larger than when I add a 0, right? So when I go from, let's say, what is this, 1 million to, let's say, 10 million and 1, instead of going from 96 to 192, it's now going from 96 to 193. So when I add a 1 at the end, it seems to be doubling and adding 1. Why does that make sense? Well, to get from 10 million and 1 to 10 million, we have to apply 1 application of the function. So we incur a cost of 1 extra operation. So at this point, we have what looks to be a general pattern, right? After appending a 0 to the number, we end up doubling the answer. And after appending a 1, the answer seems to double and increase by 1. However, you might be complaining that on the screen I have some counterexamples to this pattern. And indeed, there are two counterexamples to this pattern on the screen right now. In particular, when x is 10, we can see that when we added the 0, it didn't double. It went from 1 to 3, it tripled. And when we added a 1 to the end of 1, it again did not double and add 1. Instead, it went from 1 to 4. So our general pattern here can't be the entire picture, given that we have direct counterexamples in our sort of test case analysis so far. So what that means is we have to continue our test case bash here until we have a clearer picture of what's actually going on. So what I'm going to do is I'm going to continue analyzing more test cases until I have a clearer picture. So the next pattern I want to analyze is what happens if I do alternating zeros and ones. So we're going to write out a similar bucket of answers here. And what you can see here is we again get this pattern of almost doubling, right? So we're going from 1 to 3, from 3 to 7, from 7 to 15, from 15 to 31. So what's happening here? When I'm alternating adding zeros and ones to my number, it's doubling and adding 1. So that's a very interesting pattern. That's sort of similar to the pattern that we saw when we added a 1 to this long string of zeros. And another good test case to analyze is sort of what happens if I look at sequences of all ones. So if I have x is equal to 1, x is equal to 11, or x equals to 111. Again, we see a similar pattern of doubling, right? We go 1, 4, 10, 22, 46. It's almost doubling, but there's an extra bit here, right? So when I go from 10 to 22, that's doubling and add 2. When I go from 22 to 46, that's again doubling and adding 2. And that pattern is maintained. When I go from 46 to 94, that's 46 times 2 plus 2. So again, the pattern's maintained, and the pattern continues every time I add a 1. So sometimes when I add a 0, the answer doubles. Sometimes when I add a 0, the answer doubles and we increase by 1. Sometimes when we add a 1, the answer doubles and I add 1. And in these cases, it seems like the answer doubles and adds 2 when I add a 1. So what's going on here? The full pattern is this. It depends on the last two digits. So if the last two digits are consecutive zeros, then we simply double the number. If the previous digit was a 1 and the current digit was a 0, then we double the number and add 1. If we instead go 0, 1, we double the number and add 1. And if the previous two digits are both 1s, so we have consecutive ones, we double the number and add 2. Finding this observation is easy if you have all of this data, right? If you are willing to bash out a lot of test cases, given a sufficient amount of time, you can find this pattern. However, if you're just staring at the problem without any data to look at, it's going to be very difficult, if not impossible, to find this pattern. It's a fairly complex pattern that depends on not just one digit, but like the two most recent digits that you've added. So my recommendation, if you are going to do this test case bash, one thing that can be very helpful is before you begin your test case bash, try coding up the brute force algorithm to the question and then using that brute force algorithm in order to allow yourself to compute these test cases very quickly, right? So when I was coding this on the exam, I didn't actually have to solve very many, if any, of these test cases by hand. In fact, I don't think I solved a single test case by hand when I was doing this problem. I just immediately wrote the brute force code and then used the brute force code to generate my data, and then I analyzed that data to find a pattern. And I strongly recommend you add that approach if you find yourself having to compute dozens and dozens of test cases, right? So if you have a problem where you only need to analyze like 2 or 3 test cases to solve the problem, then maybe just analyze those 2 or 3 test cases by hand. But in cases like this, it can be very helpful to have the brute force code to allow yourself to compute the test cases quickly. Anyway, let's go take a look at the code, and then we'll wrap up the video. So in the code, I've just got the input read in here. This is one of those questions where we have t test cases per test case. So we're just looping over all of the individual test cases. And then I'm defining the integer mod to be the number that we're modding the output by. Remember, the output is going to be some massive number, so we're modding it by 1,000,000,007. This is going to be my input. I'm always adding 0 to the beginning of my input so that I don't have to worry about sort of the edge case of What about if there's only one number, right? So I'm always adding a 0 here at the beginning so that I can always look at the most two recent consecutive numbers. You don't have to do this. You can make edge cases for what happens at the very start of the string, but this is a nice way of handling it. And then we're going to have an operation count, and we're going to loop over the entire length of S, and we're just going to look at sort of the two most recent numbers. If the two most recent numbers mod 2 are 0, we're going to double our operation count. If the two most recent numbers, mod 2, are either 1, 0 or 0, 1, we'll double the number and add 1. Or if they're both 1, then we'll double the number and add 2. So there are three cases here. So case 1, two consecutive zeros. So that's both si minus 1 being 0 and s of I being 0 mod 2. Then we'll just double the operation count. And remember to mod the operation count at every step. Otherwise, the operation count is going to explode into a very massive number. Remember, the operations are growing exponentially at the moment. And then case 2, if we have two consecutive ones, we're going to take the operation count and add 2 to the, so we're going to take the operation count, double it, add 2. And then finally, if it's 1, 0 or 0, 1, we're going to take the operation count, times it by 2, add 1, take the mod. Super important at every single step to take the mod. Again, you don't want these numbers to become overwhelmingly large. And at the end, we have to recall that in our analysis here, we were only analyzing 0, 1 strings. The strings don't necessarily have to start as 0, 1s. If they start as anything other than a string of zeros and ones, we are going to first apply the operation to transform it into zeros and ones. So that's going to cost us one extra operation at the very end. So one way of just checking, did the string start as zeros and ones, is I can calculate the sum of the digits, and I can calculate the frequency of the number of ones. If the sum of the digits and the frequency of the number of ones are the same, then the string must be a string of zeros and ones. If, however, they're different, that means I've got at least one digit that is not a 0 or 1, so I'll increase my operation count by 1. That's that first step in order to go from the digits not being 0, 1 to now the digits being 0, 1. So I've got my extra operation there, then I simply return the operation count. As a little bonus, so this completes the code, but as a little bonus, we didn't actually need to write out 3 test cases here. If you are observant, you can see that the amount we're adding at each step is actually just the sum of the two previous digits, right? If we write this as maybe double the number, add 0, we can condense down these 3 cases into just one, and you can get a very nice short solution to this problem. However, I think that the solution above is a little bit clearer. So if I were you, I would analyze this code, not this one, but it might be a nice thing to look at. Thank you so much for watching, and I will see you guys in the next video. Bye bye.